Hey guys, hope everybody's doing well. It's Dr. D. We're talking about numerical measures today, continuing that discussion. Uh, and we are going to be looking at measures of central location today. So, measures of central location, right now we're really still talking about descriptive statistics. We'll get into inferential statistics in a little while. But we want to be able to summarize our data with some numbers. These are the most important measures of. So we got numerical measures, just to recap. We have numerical measures, and we're going to have a bunch of these. We're going to be measuring our data's location, where our data lie, right? So if we want to talk about, I don't know, shipping time. What is a reasonable shipping time? What are our measures of where is that located? In addition, dispersion. We're going to talk about. Okay, so best case scenario, worst case scenario, right? What would how much variation is there, right? So you tell me you think it'll get here in a week, give or take how long, right? That's what the dispersion talks about. Then we'll talk about some other measures like skewness and some other stuff, but some other measures kind of capture this. And then we'll talk about measures of relatedness between two variables. And the most important of these, probably the most important of these, is location. Right? And then location we're going to break into two parts. One will have measures of central location, and then we'll have measures of other location. Right? So central location says, okay, so we have data. It's spread out. Right? Let's say we have a bunch of points on this number line. Right? Well, where's the middle? And what do we mean by middle? If we have a bunch of points on a data line, what do we mean by middle? We're going to talk about three measures of central location today. The first one we're going to talk about the most at length is mean. Then we're going to talk about median. Finally, we'll talk about mode. And these three answer three different questions. When we say where is the middle, that has a couple different possible answers, right? One is basically if you took everything together and spread it out evenly, how much would each observation get? How much would each x equal? If they were spread out evenly, like they're not equal, right? They're dispersed, and that's why the world is an interesting place and not an undifferentiated plane. Undifferentiated planes are useful to model mathematically because then we can start talking about stuff that's different from that, and the world is different from that. But if you spread it out evenly, how much would each x equal? On average, right? On average, if we spread it out evenly. This is what we call a mean. That's this. And that's one question about the center, right? Another question would be, how much is the middle x, the x in the middle, right? Now, in terms of like income, mean is not such a good measure of the income in a country, right? Because if there's one ultra billionaire at the top and then he gets a pay raise or his stock plunges, that moves the mean around, right? It's very volatile. On the other hand, if you want to, or a better measure might be if you want to know how people are doing, is to find the person in the middle and see how much money does that guy make, right? Or that lady. We just sort everybody's income from lowest to highest, or every household. The household in the middle, that is how the average, that is the middle. That is a measure of the middle income, right? When people talk about middle income people, that's what they're talking about. And this measure of central location is called the median, right? The x in the middle, how big is that one? That's the median. So we'll talk about that. And then finally, and this is probably the least important of these, but it is another answer to the question, is if I'm going to look at an x, which is the most common, right? Which is the most common value of x? And this is mostly useful for qualitative or categorical data. As I like to say, if you are running a focus group or you're getting survey responses from your customers about the color of your new iPhone case that you're going to make, and you're getting a Kickstarter or whatever, and you're trying to get that working, you don't want to take like the hue that they give you. Let's say they choose a hue on a slider bar, you get a bunch of numbers. You don't want to find the average hue. If you find the average hue, it's going to be this color right here, right? It's going to be a nice, ugly, gray case. Maybe if people really like blue, it might be like a blue tinged gray. But that's not what people really want, right? What people really want is they may want blue or they want pink, right? They don't want you to mix these, right? And so the mode, which is this, the most common X, is really useful for categorical data because it'll tell you which of these you should choose. Maybe it's lime green, right? But it's not these three blended, right? It's not the average of these three. It's not a good idea. It would be ugly, and you would not sell very much. And so mode is useful when you want to know, okay, central location, where is the center of this, of this data? When it's categorical data, it doesn't make sense to add blue and red and green and kind of come up with an average there. So mode is that measure. Okay, now mean is the most important of these. Which is not to say that median doesn't have its uses. It sure does, and mode has its uses as well. But mean is the most important. One of the reasons this is the most important is that as we go forward, we will be doing all sorts of stuff with the mean. And so I want to spend a little bit of time talking about the mean first. So in order to talk about the mean and calculate it and do a lot of this stuff, we're going to have to use some mathematical language. And mathematical language can be daunting for a lot of people, but it has some advantages, right? One of the advantages is that it makes things shorter, right? It is very terse. Another advantage is that it is precise. The same sentence in English can be written many different ways, maybe. In math, each way should be totally convertible to another way if you're writing it. And then the last advantage is that it is abstract. What this means is that we can reuse it over and over again, right? So it's very, you might say it's formulaic because it has a lot of formulas, right? But it means that we can plug other stuff in there and get useful answers. And so in order to talk about stuff, we're going to want to build a formula eventually. But in order to be terse, precise, and formulaic, let's just say we're talking about height for now. So we're going to assign something to something else. We're going to say, well, let's let x equal height in inches. Now we can play around with x, and what we're really talking about is height in inches, but I don't have to keep writing height in inches. That is nice and terse. It's also precise because every time I talk about x, I will also be talking about height in inches. It's also abstract because you could put something else in here, right? You could put income, customer income, right, or average rent, or monthly rent, and that'll. A lot of the stuff we do will work with that as well. You could put favorite color in here, and some of the stuff we do will not work so well, right? Because as we talked about in the data scale section, there's some stuff it doesn't make sense to do to some types of variables. But as long as we have, in this case, this is a ratio scale variable. As long as we have a ratio scale variable, all the stuff we're going to do will hold. So ratio scale, yay. Okay, so that's our first sentence in mathematical language. You can put a period after it if you want. Now what we're going to do is we're going to define, for a sample of size n, the sample mean, and then I'm going to put value of x in parentheses. If we only have one variable, usually we don't have to point out what is the sample mean of, and so often I'll just refer to this as a sample mean. But when we get to two variables, if we have an x and a y and a z, that's three variables for those of you keeping track, then we're going to want to be more specific about what we're talking about. So the sample mean can be found like this. And you've done this before, right? The common English way to do it is to take all the numbers and add them up and divide by however many there are, right? Now in mathematics, the way we write it is x bar, that's our sample mean, equals the sum from I equals 1 to n of x sub I, all divided by n. Okay. That's a pretty simple formula once you understand the notation. And so let's break it apart a little bit. Let me get us a little bit more space over here. And we'll play with it. We'll take it to pieces. Let's see. So we know what this stuff is, right? This right here, that's a fraction bar. And that just means we're going to divide, right? If you don't know this, there's a handy little piece of trivia. The division symbol, you've seen before. This is just a fraction bar with something on top and something on the bottom, right? What do you know? It looks exactly like this if you squint and you can't really see what's on top and what's on the bottom, right? So 3/5 is something on top, something on the bottom. It's 3 divided by 5, and so that's where that comes from. Okay. This right here, we've talked about this before. You may not have seen that video, so I'll just define it. N is our sample size, which is our number of observations, right? It's how many elements we're looking at any given time, or at a specific time. Alternatively, if it's time series data, it might be the number of measurements we have of one element, but it's our sample size, the number of observations. Okay, so that's the bottom half. This x bar right here, we already know what that is because we just defined it. It's the sample mean. Ta-da, that's x bar. So what's on top? Well, let me draw it a little bit bigger just so you can kind of see it. So what we have here is we have a big sigma, and I equals 1 is a subscript, and n is a superscript. So this symbol has a subscript, which means underwritten, right? Writing underneath, and a superscript, writing on top. It's a big Greek letter, and it is a summation symbol or a summation operator. Sometimes these are called big operators. And it tells you what to do. It's like a for next loop if you're familiar with computer science. It says start with I equals 1, and then proceed through all the i's till you get to n, till you get to I equals n, and then sum, right? Add up. The symbol itself is called sigma. It's a capital sigma, and it's a summation operator. And so that's what it tells us. It tells us take some stuff, in particular, take anything over here in this direction, all of this stuff, right? Do stuff to it first, and then you should end up, if you wouldn't use this, if you should end up with a series of something with an index of 1, something with an index of 2, something with an index of 3, until you get to something with an index of n. Once you get those, what you want to do is add them up, right? 1 plus 2, this thing sub 1 plus this thing sub 2 plus this thing sub 3 over and over again until you get to this thing sub n. And then you're done. In this case, what it's telling us to add up is the stuff directly to the right, which is just x sub I. So what is x sub I? Well, we know what x is, right? I defined it up here. X is a height. Right? So x is height. So what is I? Well, I is an index. When we want to measure people's height, we don't want to double count anybody, we don't want to skip anybody, right? And so one thing we can do is we can give everybody a deli ticket, right? Just like you take a number, right? They give you a little number and you sit there, you're holding on to your number, and your number is 12. And so they call X1, and person holding ticket 1 goes up and gets their height measured. They say X2, person holding ticket 2 goes up and gets their height measured. If your number is X12, or if your number is 12, then X12 is your height, right? If your number is not 12, let's say they call up X13, this is the height of person 13. Right? And so this is just saying, get everybody's height from 1 to n, right? Call up person 1, call up person 2, and get those heights. Once you have them, then what you want to do is start with 1 and add them until you get up there, right? Until you get all the way up. So what does this mean? Well, let's just say, for example, that n was 3. Well, then this sum would be the sum from I equals 1 to 3 of x sub I. So what is that sum? Well, that is just x1 plus x2 plus x3. Right? You can see that this, although it's maybe a little daunting if you're not familiar with summation symbols, is shorter already. Oops. Shorter already than this over here. And if n equals 500, then oh boy is that a lot shorter, right? And so this is a way to, this is a compressed notation, right? It just makes it shorter to write. The other advantage of it is that in this case we have a sum of 3 numbers, but this sum, this notation, if this is an n, if this is, if this were n instead, works for any n greater than 0, right? That's finite, I suppose. Any whole number greater than 0. You wouldn't go from I equals 1 to 2.7, right? But when we're counting people, we're always going to have a whole number anyway. So that's the formula. Let me rewrite the formula down here without such a mess around it. X bar equals the sum from I equals 1 to n of x sub I all over n. There we go. Cool. So let's see. Let's do an example. Let me see if I can copy and paste this in here. That would be handy if I could. Yeah, I can. What do you know? There we go. So we have a bunch of people with some heights. Oop, don't want to do that. There we go. Cool. So we have 5 people's heights. I just made them up. You can tell by the fact that they have names that start with A, B, C, D, and E. But we're going to be able to calculate the average height of this group of people. So what is the average height of this group of people? Well, let's use our formula. What we've done is we've taken Alex, Brandy, Carla, Devin, and Aaron, and we've given them each a ticket. And now that they each have a ticket, we will be able to calculate their average height. I'm trying to go. All right, good enough. What is their average height? Well, we got to follow this formula. We take x1, that's 66, plus x2, that's 64, plus x3, that's 73, plus x4, that's 60, plus x5, that's 57, and we add these together, right? So we have our xi's, check. Now we're doing the summation, check. Add these up, what do you get? You get 6 and 4 is 10, plus 3 and 7 is 20. 0, carry the 2. 2 and 6 is 8, and 6 is 14, and 7 is 21, and 6 is 27, and 5 is 32. 320. So that's our sum. And so we could write, just so you're comfortable with this, the sum from I equals 1 to 5 of x sub I equals 320, right? Because this is just x1 plus x2 plus x3 plus x4 plus x5, which is what this is, and so we get 320. Okay, so now we got our numerator. This numerator, let me make a big equal sign, this is 320. What's our denominator? Well, n is just how many people we have. It turns out it's the biggest number of your indexes, right? Because you just 1, 2, 3, 4, 5. Counting for us right there. So 320 divided by 5 is our x bar. 320 divided by 5, that's going to be 640 divided by 10, multiplied by 2, which is 64. So the average height, the mean height in this group of people is 64 inches, right? That's how tall they are on average. And so we can see that Alex is taller than average, as is Carla. Devin and Aaron are both shorter than average, and Brandy is right there, smack at the average. But that's how we calculate a mean. Okay. Now that's a sample mean, right? Because we only had 5 people. What if we want to talk about the height of every person that ever exists, or every person on Earth? Well, in that case, instead of talking about a sample, we're talking about the population, the entire population, right? And ultimately, usually we will care more about the population mean, right? We're going to use samples to try to say something about the population. The population mean is referred to with the letter mu. It's a Greek letter. Often when we talk about the population, we'll be using Greek letters. And this is the symbol for it, mu. I guess maybe the first leg should be longer. I think that's right. Mu equals, what does mu equal? Well, mu now, we're still going to be basically adding up all of the heights and then dividing by how many there are. But instead of working with a sample, we're going to work with the entire population. So we take I equals 1 to big N, because that's our population size of x sub I, all divided by big N. Cool. Now that is a more important number than x bar in some sense, because it's the true underlying value of the entire population. It's also a pain because we can't actually calculate it because n is too big. That's why we use statistics in the first place. You have to count every single member of the population, and that's just not feasible. Cool. So that's, but we do care about it, mu. We're going to talk more about mu later. Usually we won't be calculating it though. Okay, so now that you've seen this notation here and the notation down here, what are some other ways you might see this just so you don't feel daunted? Well, sometimes, since in this case we're adding up all of the i's, right? Any I you happen to find, right? We're counting everybody we have. Sometimes instead of saying which i's we want, we'll just put the little index I here, and then put xi over n. Right? And that's the same. In this case, it tells us explicitly where we're looping, and this just says loop over all of them, right? Over all of the i's. If you have an I lying around, throw that one in, add them all together, and then you divide by n. So that's another notation that means exactly the same thing. Alternatively, because we're adding up all of our indices, right, and there's only one index, it's just I, there are no j's, there are no k's, and those are common letters for indices, but we only have one in this case because we only have rows and no columns. We might use this other symbol, the shortened version, which is just x is equal to the sum of x sub I over n. The basic premise here is that the index we want to use should be obvious, right? It's under the x, so you know that's the index you care about. Just add, find the index and then add them up. This, still have a summation operator, but this is about as tersely as you'll ever see this written. It is a little more terse, but it's less precise, and so you trade off. There's a little bit of a trade-off for precision. Okay, so that is one measure of central location. That's our mean, and that is the most important measure of central location. But what else do we have? Well, the next one I told you about is the median, right? The median is the value of the middle observation. Now there are two possible cases here, right? One is n is odd, right? Like in the case we had right here. Up here n was 5. And in this case, the median is going to be the value of the middle observation. Well, what is that? Well, first we have to sort the data, and then we're going to have to find the middle one. So let's sort this. We're going to have 57, 60, 64, 66, 73. These are in order, so I use parentheses instead of brackets. And the middle one, well, we got 1, 2, 3, 4, 5. That's this one right here. And when you have small data sets, that's relatively easy to find the middle one, right? And we only have 5 numbers here. But if our data set is a little bit larger, it's useful to keep in mind that there's a rule you can use. It's going to be the median is x sub n plus 1 over 2, once they're in order, right? In this case, n equals 5. And so the middle observation is going to be observation n plus 1 over 2, which will always give you an even number, right? Because you have an odd number plus 1 gives you an even number. Divide by 2 will get you halfway, and this is 3, right? So that's the index, the third number. But if n equals, say, 1025, for example, well then, which one do we want? Well, it'd be a pain to try to count from both sides. So add 1, you get 1026 divided by 2. That's going to be 513, right? So x513 is your median. So that's how you calculate the median. If n is odd, what if, however, n is even? Well, if n is even, then there is no middle observation, right? So let's say, for example, that we had one more person added to this. So now we have these heights. What do we want? 57, 60. Let's say we add somebody who's 5'7", 66, 67, 73. Okay, well now if we try to find the middle person, there is no middle person, right? Because we have 1, 2, 3, 4, 5, 6. That's an even number, and the middle falls right in here. Well, in this case, what we want to do is we want to take the median is going to be the average of the middle two. It's the mean of the middle two observations. So the average of 64 and 66, you can eyeball it and say 65, but the way to calculate it is 64 plus 66 divided by 2 equals, what is that, 130? Yep, 130 over 2 equals 65. And once again, this is easy if you have a relatively low n, but if you have a large n, then what you want is you want the average of x sub n over 2 and x sub n plus 2, the quantity over 2, right? And in this case, that's n over 2 is 3, n plus 2 over 2 is 4, and so it's going to be the average of those. But if, for example, n equals 1024, then what you're going to want is x 512 and x 513. You're going to want the average of these two once you've sorted them. So that can be useful to know. Cool, so that's how you calculate medians. Pretty straightforward. The last one, the mode. Well, the mode is just the most commonly occurring value of x. Most frequently occurring value of x. In this case, we don't have any modes, or we have they're all the mode, right? So we can have multiple modes are possible. in general, if you have a data set that's of a reasonable size, and in this case these are very unreasonably small, you won't exactly have multiple modes. Although sometimes you might have two modes, and when we have two modes, we refer to that data set as bimodal. And that's true even if they're not exactly the same. Well, the term bimodal is used. So let's say you do a histogram or a even with categorical data, let's say you have 1, 2, 3, 4, 5 shades of something, and you have something, you do a bar chart and it looks like this. And this is still a bimodal data set, right? These could be political candidates or something, because this is tall and this is tall and all of the rest of them are short, and so people might refer to this as a bimodal data set. But yeah, technically this would be the mode. And sometimes you might say there are two modes or there are three modes, and they are 1, 5, and 2 or something like that. So there you go. So the three measures of central location we have then are mean, which is the most important, median. Oh, and I forgot to mention the advantage of the median. One of the real advantages of the median is that maybe I did mention it, that if a billionaire's income goes up and down, then the median income will change a lot, or the mean income will change a lot, but the median won't. So the mean is susceptible to the fluctuations in extreme values, whereas median doesn't move around as much, so it's a little bit more stable. It's particularly nice. It's useful for skewed data sets. So mean and median, if you have data that looks like this, like that, kind of symmetrical, then mean and median usually will come close together. But in general, if you have data sets that are skewed, right, then the mean might be pulled down by some of these very extreme low values, whereas the median is going to have half of the weight of the data set on one side and half of the weight. The median is probably actually more like here. So this might be X bar and this might be your median. And so skewed data sets, the median is a better measure than the mean of where the center is, really. Then finally we have the mode, which is useful for categorical data. So there you go. Those are our measures of central location. We're going to talk about other types of location soon, because often we want to know about the top 10% or the lowest quarter or something like that. But these are the most important. So I hope you found that useful. Let me know if you have any questions or comments in the comment thread. And I'll see you guys next time. Thanks.